Okay, welcome everybody. This is the homework one for CS2340, and I will be reading the paper No Silver Bullet, Essence and Accident in Software Engineering. Um, I mean, I would recommend turning down the audio a little bit because I am going to be holding the mic here this entire time. So, all right, let's get right into it, shall we? Um, this is no silver bullet. Essence is accident in software engineering. This is written by Frederick P. Brooks Jr., who is at the University of North Carolina at Chapel Hill. And the first quote is: "There is no single development in either technology or management technique, which by itself promises even one more order of magnitude improvement within a decade in productivity, in reliability, and in simplicity." I'm going to quickly turn off this light because this is blaring straight into the camera. Okay, that's better. All right, let's jump right into it. With the abstract. All software construction involves the essential tasks, the fashioning of complex conceptual structures that compose the abstract software entity and accidental tasks. The representation of these abstract entities in programming languages and the mapping of those onto machine learning languages within space and speed constraints. Most of the big past gains in software productivity have come from removing artificial barriers that have made the accidental tasks inordinately harder, such as severe hardware constraints, awkward programming languages, lack of machine time. How much of what software engineers now do is still devoted to the accidental as opposed to the essential? Unless it is more than 9 out of 10 of all effort, shrinking the accidental activities to zero time will not give an order of magnitude improvement. Therefore, it appears that the time has come to address the essential parts of the software task, those concerned with fashioning abstract conceptual structures of great complexity. I suggest exploiting the mass market to avoid constructing what can be bought, using rapid prototyping as a part of planned iteration in establishing software requirements, growing software organically, adding more and more functions to the system as they are run, used, and tested, and identifying and developing the great conceptual designers of the rising generation. Now, it seems like this paper is generally going to be about how to address a lot of the problems that we currently have with software engineering. I myself have been an experienced game developer working with multiple Minecraft modding teams over the years, as well as the GTVG Dev club. And a lot of the points that I see here that are very important to what I have done over the past few years is stuff like this. It's growing software organically, adding more and more functions to the system as they are unused and tested. This is the essentials of how a video game is developed, right? So, um, exploiting the mass market to avoid constructing what can be bought. We don't want artists in VG Dev to be consistently just making random stuff that they can't um, that they can't make, right? We want to be able to use as much stuff from online as we can, find free stuff that we can use. So, from what I can tell within this abstract, this is stuff that is going to be very important for a lot of software engineers, video game developers, anything in that realm. So, let's jump right into the introduction. Of all the monsters who fill the nightmares of our folklore, none terrify more than werewolves. Because they transform unexpectedly from the familiar into horrors. For these we seek bullets of silver that can magically lay them to rest. The familiar software project has something of this character, at least as seen by the non-technical manager, usually innocent and straightforward but capable of becoming a monster of missed schedules, blown budgets, and flawed products. So we hear desperate cries for a silver bullet, something to make software costs drop as rapidly as computer hardware costs do. But as we look into the horizon of decade hence, we see no silver bullet. There is no single development in either technology or management technique, which by itself promises even one order of magnitude improvement in productivity, in reliability, and in simplicity. In this chapter, we will try to see why, by examining both the nature of the software problem and the properties of the bullets proposed. Skepticism is not pessimism, however. Although we see no startling breakthroughs and indeed believe that they're such to be inconsistent with the nature of software, many encouraging innovations are underway. A disciplined, consistent effort to develop, propagate, and exploit them should indeed yield an order of magnitude improvement. There is no royal road, but there is a road. The first step towards management of disease was replacement of demon theories and humorous theories by the germ theory. That very step, the beginning of hope, in itself dashed all hopes of magical solutions. It told workers the progress would be made stepwise at a great effort, and that a persistent, unremitting care would have to be paid to a discipline of cleanliness. So it is with software engineering today. He makes some interesting comparisons here, I must admit. A lot of these comparisons are ways that I have not thought of software despite developing it for such a long time. But I think some of them do have some element of truth to it, especially this idea here. But I think it needs a bit more time to simmer in my head, per se. All right. Does it have to be hard? Essential difficulties. Not only are there no silver bullets now in view, the very nature of software makes it unlikely that there will ever be any. No inventions that will do for software productivity, reliability, and simplicity what electronics, transistors, and large-scale integration did for computer hardware. We cannot expect ever to see twofold gains every 2 years. First, we must observe the anomaly that is not the software progress is so slow, but the computer hardware progress is fast. No other technology since civilization began has seen 6 orders of magnitude price performance gain in 30 years. And no other technology can choose one to take the gain in either improved performance or in reduced costs. These gains flow from the transformation of computer manufacture from an assembly industry to a process industry. Second, we see what rate of progress we can expect in software technology. Let's just examine its difficulties. Following Aristotle, I divide them into essence. The difficulties inherent in nature of the software and accidents, those difficulties that today attend in production, but that are not inherent. The accidents I discuss in the next section. First, let us consider the essence. The essence of a software entity is a construct of interlecting concepts, data sets, relationships among data items, algorithms, and invocations of functions. This essence is abstract in that the compound construct is the same under many different representations. It is nonetheless highly precise and richly detailed. I believe the hard part of building software to be the specification, design, and testing of this conceptual construct, not the labor of representing it and testing the fidelity of the representation. We still make syntax errors, to be sure, but they are fuzz compared to the conceptual errors in most systems. If this is true, building software will always be hard. There is no inherent silver bullet. Let us consider the inherent properties of this irreducible essence of modern software systems: complexity, conformity, changeability, and invisibility. It's interesting. Although we haven't gone into the meat and potatoes yet, it has revealed a lot to us. Where was it? I'm trying to find where he said that. Oh yeah. As a computer engineer, this is extremely fascinating to me. I did know that this existed, but I didn't know the exact numbers of how fast computer hardware has been progressing. But yeah, that is a thing, right? Like we see that basically every single year. Like you either look at the iPhone or CPU or like CPUs from like Ryzen, AMD, or like Intel, like the Intel iCPUs, and like you're seeing that like they increase in like performance by like 20% each year. But software, like honestly, like the only big, huge like breakthrough that we've had in like the last however often has been AI. So it's definitely interesting to see. Um, Software has always been the harder of the two because hardware is just like there's clear ways to make stuff more efficient. It's and like especially for computer hardware, a lot of it just comes down to making stuff smaller. So let's move on. Apologies. Complexity. Software entities are more complex for their size than perhaps any other human construct, because no two parts are alike, at least above the statement level. If they are, we make the two similar parts into one, a subroutine, open or closed. In this respect, software systems differ profoundly from computers, buildings, or automobiles where repeated elements abound. This is what I was talking about. Digital computers are themselves more complex than most things people build. They have a very large number of states. This makes conceiving, describing, and testing them very hard. Software systems have orders of magnitude more. I lost my place. Give me a second. Software systems have orders of magnitude more states than computers do. Likewise, a scaling up of software entity is not merely repetition of the same elements in larger size, it is necessarily an increase in the number of different elements. In most cases, the elements interact with each other in some nonlinear fashion, and the complexity of the whole increases much more than linearly. The complexity of software is an essential property, not an accidental one. Hence, descriptions of a software entity that abstract away its complexity often abstract away its essence. Give me 1 second. Mathematics and the physical sciences made great strides. Sorry. I'm just trying to adjust the audio of the video right now. Hence, descriptions of a software entity that abstract away its complexity often abstract away its essence. Mathematics and physical sciences made great strides for 3 centuries by constructing simplified models of complex phenomena, deriving properties from the models, and verifying those properties experimentally. This worked because the complexities ignored in the models were not essential properties of the phenomena. It does not work when the complexities are the essence. Many of the classical problems of developing software products derived from this essential complexity and its nonlinear increased with size. From the complexity comes the difficulty of communication among team members, which leads to product flaws, cost overruns, schedule delays. From the complexity comes the difficulty of enumerating much less understanding all the possible states of a program, and from that comes the unreliability. From the complexity of the functions comes the difficulty of invoking those functions, which makes programs harder to use. From complexity of structure comes the difficulty of extending programs to new functions without creating side effects. From the complexity of structure comes the unvisualized state that constitutes security trapdoors. Not only technical problems, but management problems as well come from the complexity. This complexity makes overview hard, thus impeding conceptual integrity. It makes it hard to find and control all the loose ends, and it creates the tremendous learning and understanding burden that makes personnel turnover a disaster. This is an interesting point. I think that I have seen this in person, particularly like when I was onboarding for RoboJackets. Um, it felt like everything that I had learned about computer science was just completely like thrown out the window because nothing really applied because they already had their like predetermined functions and what they did in terms of how the system was built. So by the time that I got there, they basically like had a system built, but I didn't know how to use the system. So yeah, I mean like this is like just the sort of thing where really just have to like learn as fast as possible the moment you get into like an internship or co-op that involves like software like this. All right, next section. Conformity. Software people are not alone in facing complexity. Physics deals with terribly complex objects even at the fundamental particle level. The physicist labors on, however, in a firm faith that there are unifying principles to be found, whether in quarks or in unified field theories. Einstein repeatedly argued that there must be simplified explanations of nature because God is not capricious or arbitrary. No faith comforts the software engineer. Much of the complexity he must master is arbitrary complexity, forced without rhyme or reason by the many human institutions and systems to which his interfaces must conform. These differ from the interface to interface from time to time not because of necessity, but only because they were designed by different people rather than by God. In many cases, the software must confirm because it has the most recently come to the scene. In others, it must confirm because it is perceived as the most comfortable. But in all cases, much complexity comes from conformation. Okay, sure. To other interfaces. This cannot be simplified out by any redesign of the software alone. This is definitely something that I've seen in algorithms. Algorithms is a class that takes computer science to like the actual point where like it lives up to its name as a science. So, I mean, as a computer engineer, learning that fundamental level is definitely interesting, but it feels arbitrary a lot of the time. It like as the paper says, right? It feels like that I'm learning something that someone created rather than the fundamental properties of it, how a computer works, right? It's not like this is like the one way of how it works. It's like we made this thing to work in this situation and another thing to work in a different situation. So it's just like it makes the class hard, right? That's what makes computer science difficult at the end of the day. All right, next section. Changeability. The software entity is constantly subject to pressures for change. Of course, so are buildings, cars, and computers. But manufactured things are infrequently changed after manufacture. They are superseded by latter models, or essential changes are incorporated in later serial number copies of the same basic design. Callbacks of automobiles are really quite infrequent. Field changes of computers somewhat less so. Both are less frequent than modifications to fielded software. Partly this is because the software in a system embodies its function, and the function is the part that most feels the pressure of change. Sorry. Partly it is because software can be changed more easily. It is the pure thought stuff, infinitely malleable. Buildings do in fact get changed, but the high costs of change, understood by all, serve to dampen the whim of the changers. All successful software gets changed. Two processes are at work. As a software product is found to be useful, people try it in new cases, at the edge of or beyond the original domain. The pressures for extended function come chiefly from users who like the basic function and invent new uses for it. Second, successful software also survives beyond the normal life of the machine vehicle for which it is first written. If not new computers, then at least new disks, new displays, new printers come along, and the software must be confirmed to its new vehicles of opportunity. In short, the software product is embedded in a cultural matrix of applications, users, laws, and machine vehicles. These all change continually, and their changes inexorably force change upon the software product. Now, in video games, like they get updated because they need to keep the game fresh, right? And they need to add new stuff to keep people hooked on the game. But a lot of the other stuff comes from purely the way people use a piece of software, right? Like nowadays, like after the explosion of AI, we're seeing tons of people, tons of sites like implementing an AI summaries or AI like question bots to help them like do their online errands, right? Along other stuff like that, there's other stuff that like the front end revolution, where it's where the way we look at software, the way we perceive like how stuff should be designed, completely changed a few years ago. Well, more than a few years ago. That was like 10 years ago. But it really comes down to just like what the paper is saying, right? We want software to function in the way we currently want it to function, right? And because it's easy to change, we have to we have to make it so that we can go back and change it again later. But yeah, that's it. I think that a lot of these points are very true to the difficulties of software, and what really makes it just like something that beyond just the classroom takes practice. All right, last point. Invisibility. Software is invisible and unvisualizable. Geometric abstractions are powerful tools. The floor plan of a building helps both architect and client evaluate spaces, traffic flows, and views. Contradictions become obvious, omissions can be caught. Scale drawings of mechanical parts and stick figure models of molecules, although abstractions, serve the same purpose. A geometric reality is captured in a geometric abstraction. The reality of software is not inherently embedded in space, hence it has no ready geometric representation in the way that land has maps, silicon chips have diagrams, computers have connectivity schematics. As soon as we attempt to diagram software structure, we find it to constitute not one, but several general directed graphs, superimposed upon one another. The several graphs may represent the flow of control, the flow of data, patterns of dependency, time sequence, and namespace relationships. These are usually not even planar, much less hierarchical. Indeed, one of the ways of establishing conceptual control over such structure is to enforce link cutting until one or more of the graphs becomes hierarchical. In spite of progress in restricting and simplifying the structures of software, they remain inherently unvisualizable, thus depriving the mind of some of its most powerful conceptual tools. This lack not only impedes the progress of the process of design within one mind, it severely hinders communication among minds. Now I'm going to use another example from algorithms on this. When you take a physics class, right, or when you take a math class, right, you're able to visualize everything that they tell you, right? Physics, you could think of the particles in your mind. You know the properties of the particles, so you can think about how they behave. In a math class, you can think of especially stuff like multivariable calculus or differential equations. You can think about like how the different variables interact with each other, right? Oftentimes they'll also ask you application questions, which make it easier to think about. But software, especially in a more theoretical aspect, such as algorithms, is completely different, right? This is a subject that is unique in its way, that other than the computer code in front of you, other than the pseudocode, right? There's no way to really visualize it unless you run an example or test case on the whatever idea that you're coming up with, right? Like if you come up with an algorithm to solve a problem, and then you find out that it does work based off the example that you tried it in, right? But that doesn't mean that it'll work for all examples, right? And that also doesn't mean that it's the time complexity that you want out of it, right? So software's hard. And the paper's correct, to say the least. I'm going to stop this recording here. And I'm going to piece together 4 recordings. We are at page 4 right now, so we will start on page 5 in the next recording. Okay, well, sorry. Let us continue. Okay, past breakthroughs solved and accidental difficulties. If we examine 3 steps in software technology that have been the most fruitful in the past, we discover that each attacked a different major difficulty in building software, but that but they have been the accidental, not the essential difficulties. We can see the natural limits to the extrapolation of each such attack. High-level languages. Surely the most powerful stroke for software productivity, reliability, and simplicity has been the progressive use of high-level languages for programming. Most observers credit the development with at least a factor of 5 in productivity and with concomitant gains in reliability, simplicity, and comprehensibility. What does a high level language accomplish? It frees a program from much of its accidental complexity. An abstract program consists of conceptual concepts, operations, data types, sequences, and communication. The concrete machine is concerned with bits, registers, conditions, branches, channels, disks, and such. To the extent that a high-level language embodies the construct wanted in the abstract program and avoids all lower ones, it eliminates a whole complexity that was never inherent in the program at all. The most a high-level language can do is to furnish all the constructs the programmer imagines in the abstract program. To be sure, the level of our sophistication in thinking about data structures, data types, and operations is steadily rising, but at an ever decreasing rate, and language development approaches closer and closer to the sophistication of users. Moreover, at some point, the elaboration of a high level language becomes a burden that increases, not reduces, the intellectual task of the user who rarely uses the esoteric constructs. Now we see that because this is because like it is a high level language, right? Like something like Python or something like Java, right? Python in particular, it really simplifies the use and process of programming, right? Um, to be fair, I haven't taken a course in assembly or C yet, but I will be taking one next semester. So um, at that point, I'll have to be able to compare. But as of now, like my entire software education has been with high level languages, so that tells you something. Next up, time sharing. Most observers credit time sharing with a major improvement in the productivity of programmers and the quality of their product, although not so large as that bought by high level languages. Time sharing attacks a distinctly different difficulty. Time sharing preserves immediacy and hence enables us to maintain an overview of complexity. The slow turnaround of batch programming means that we inevitably forgot the minutiae, if not the very thrust of what we were thinking about when we stopped programming, and called for compilation and execution. This interruption of consciousness is costly in time, for we must refresh. The most serious effect may well be the decay of grasp of all that is going on in a complex system. Slow turnaround, like machine language complexities, is an accidental rather than an essential difficulty of the software progress. The limits of the contribution of time sharing derive directly. The principal effect is to shorten system response time as it goes to zero. At some point, it passes the human threshold of noticeability, about 100 milliseconds. Beyond that, benefits are to be expected. No benefits are to be expected, sorry. I honestly don't have too much to say about this one, but this is an interesting point at the end here. Once we get to that point, like, is there a point to continue attempting to improve how much time a system takes? Could be yes, could be no. Next, unified programming environments. Unix and Interlisp are the first integrated programming environments to come into widespread use, are perceived to have improved productivity by integral factors. Why? They attack the accidental difficulties of using programs together by providing integrated libraries, unified file formats, and and filters. As a result, conceptual structures that principle could always call, feed, and use one another can indeed easily do so in this practice. This breakthrough in turn stimulated the development of whole tool benches, since each new tool could be applied to any program by using the standard formats. Because of these successes, environments are the subject of much of today's software engineering research. We will look at their promise and limitations in the next session. Now, a lot of developers use an environment such as Linux today to develop, especially those working with more physical aspects such as robotics, um, actual just research, um, stuff along those lines, right? And this is definitely probably the reason for it. So yeah. Hopes for the silver. Now let us consider the technical developments that are most advanced as potential silver bullets. What problems do they address? Are they the problems of essence, or are they reminders of our accidental difficulties? Do they offer revolutionary advances or incremental ones? ADA and other high-level advances. One of the most touted recent developments in the programming language, ADA, a general-purpose high-level language of the 1980s. ADA indeed not only reflects the evolutionary improvements in language concepts, but embodies features to encourage modern design and modularization concepts. Perhaps the ADA philosophy was more of an advance than the ADA language, for it is the philosophy of modularization of abstract data types, hierarchical structuring. ADA is perhaps overrich, the natural product of the process by which requirements were laid on its design. That is not fatal. For subset working vocabularies, it can solve the learning problem, and hardware advances will give us the cheap MIPS to pay for the compiling costs. Advancing the structuring of software systems is indeed a very good use for the increased MIPS of our dollars will pay. Operating systems loudly decreed in the 1960s for their memory and cycle costs have proved to be an excellent form in which to use some of the MIPS and cheap memory bytes of the past hardware surge. Nevertheless, ADA will not prove to be the silver bullet that slays the software productivity monster. It is, after all, just another high-level language, and the biggest payoff from such languages came from the first transition up from the accidental complexity of the machine into the more abstract statement of step-by-step solutions. Once those accidents have been removed, the remaining ones are smaller, and the payoff from the removal will surely be less. I predict that a decade from now, when the effectiveness of ADA is assessed, it will be seen to have made a substantial difference, but not because of a particular language feature, nor indeed because of all of them combined. Neither will the new ADA environment prove to be the cause of the improvements. ADA's greatest contribution will be that switching to it occasioned training programmers in modern software design techniques. I've actually never heard of this. Um, it's crazy that even in the 1980s they had high level languages, but I think the fact that I've never heard of it, and that a lot of you watching have probably never heard of it, that shows that this was not the breakthrough that it may have been presented to be at the time. But we do have one below us that we definitely still use today. Object-oriented programming. Many students of the art hold out more hope for object-oriented programming than any of the other technical fads of the day. I am among them. Mark Sherman of Dartmouth notes that we must be careful to distinguish two separate ideas that go under that name: abstract data types and hierarchical types. Also called classes. The concept of the abstract data type is that an object's type should be defined by a name, a set of proper values, and a set of proper operations rather than its storage structure, which can be hidden. Examples are ADA packages with private types or modulus modules. Hierarchical types such as Simula 67's classes allow the definition of general interfaces that can be further refined by providing subordinate types. The two concepts are orthogonal. There must be hierarchical without hiding and hiding without hierarchies. Both concepts represent real advances in the art of building software. Each removes one or more accidental difficulties from the process, allowing the designer to express the essence of his design without having to express large amounts of syntactic material that add no new information content. For both abstract types and hierarchical types, the result is to remove a higher order sort of accidental difficulty and allow a higher order expression of design. Nevertheless, such advances can do no more than to remove all the accidental difficulties from the expression of the design. The complexity of the design itself is essential, and such attacks make no change whatever in that. An order of magnitude gain can be made by object-oriented programming only if the unnecessary underbrush of type specification remaining today in our programming language is itself responsible for the 9/10 of the work involved in designing a program product. I doubt it. Now, object-oriented programming is definitely something that is one of the centerpieces of programming today still. Like the second introductory computer science course is called object-oriented programming, right? But really, it's just a matter of that it comes down to is just that it kind of was the natural direction that programming should have gone in. Um, I mean, today we treat it like it's not even there, right? And software is still just as difficult as it was before, right? So the difficulty has moved from repeating the code to create things to thinking of the ideas of creating those objects themselves, and that means that instead of removing complexity from the process of building software, you're just changing where it's concentrated. Artificial intelligence. Now, this one might be interesting. Many people expect advances in artificial intelligence to bring the revolution a breakthrough that will give an order of magnitude gains in software productivity and quality. I do not. To see why, we must dissect what is meant by artificial intelligence and then see how it applies. Parnas has clarified the terminological chaos. Two quite different definitions of AI are in common use today. AI 1, the use of computers to solve problems that previously only could be solved by applying human intelligence. And AI 2, the use of a specific set of programming techniques known as a heuristic or rule-based programming. In this approach, human experts are studied to determine what heuristics or rules of thumb they should use in solving problems. The program is designed to solve a problem the way the humans seem to solve it. The first definition has a sliding meaning. Something can fit the definition of AI 1 today, but once we see how the program works and understands the program, we will not think of it as AI anymore. Unfortunately, I can't identify a body of technology that is unique to this field. Most of the work is program specific, and some abstraction or creativity is required to see how to transfer it. I completely agree with this critique. The techniques applied for speech recognition seem to have little in common for those used in image recognition, and both are different from those used in expert systems. I have a hard time seeing how image recognition, for example, will make any appreciable difference in programming practice. The same is true of speech recognition. The hard thing about building software is deciding what to say, not saying it. No facilitation of expression can give more than marginal gains. Expert systems technology AI2 deserves a section of its own. This point is odd. I I feel like he is addressing this idea of speech recognition and facial recognition systems just for the heck of it. Like, obviously, they're not going to help with programming. That's like extremely obvious, in fact. Like, that's like saying that like a spoon is going to help you um like finish your assignment. Um but it's just sure, all right. But I think like when we think about artificial intelligence and programming, we think more about like something along the lines of ChatGPT, right? Which I hope he's going to address in this next section. The most advanced part of the artificial intelligence art and the most widely applies is the technology for building expert systems. Many software scientists are hard at work applying this technology to the software building environment. What is the concept and what are the prospects? An expert system is a program containing generalized inference engine and a rule base designed to take input data and assumptions and explore the logical consequences through the inferences derivable from the rule base, yielding conclusions and advice offering to explain its results by retracing its reasoning for the user. The inference engines typically can deal with fuzzy or probabilistic data and rules in addition to purely deterministic logic. Such systems offer some clear advantages over programmed algorithms for arriving at the same solutions to the same problems. Inference engine technology is developed in an application independent way and then applied to many uses. One can justify much more effort on the inference engines. Indeed, that technology is well advanced. The changeable parts of the application peculiar materials are encoded in the rule base in a uniform fashion, and tools are provided for developing, changing, testing, and documenting the rule base. This regularizes much of the complexity of the application itself. Edward, I'm going to butcher that, Fagenbaum says that the power of such systems does not come from ever fancier inference mechanisms, but rather from ever richer knowledge bases that reflect the real world more accurately. I believe that the most important advance offered by the technology is the separation of the application complexity from the program itself. How can this be applied to the software task? In many ways, suggesting an interface of rules, advising on testing strategies, remembering but type frequencies, offering optimization habits, etc. Consider an imaginary testing advisor, for example. In its most rudimentary form, the diagnostic expert system is very much like a pilot's checklist, fundamentally offering suggestions as to possible causes of difficulty. As the rule base is developed, the suggestions become more specific, taking more sophisticated account of the trouble system's symptoms reported. One can visualize a debugging assistant that offers very generalized suggestions at first, but as more and more systems structure is embodied in the rule base, comes more and more Jesus, more and more particular in the hypothesis is generates and the test it recommends. Such an expert system may depart radically from the conventional ones in it, then its rule base should probably be hierarchically modularized. Say that 10 times fast. In the same way the corresponding software product is. So that the product is modularly modified, the diagnostic rule can be modularly modified as well. The work required to generate the diagnostic rules is work that will have to be done anyway in generating the set of test cases for the modules and for the system. If it is done in a suitably general manner with a uniform structure for rules and a good interface inference engine available, it may actually reduce the total labor of generating bring up test cases, as well as helping in lifelong maintenance and modification testing. In the same way, we can postulate other advisors, probably many of them, and probably simple ones for the other parts of the software construction task. Many developers stand in the way of early realization of useful expert advisors to the program developer. A crucial part of our imaginary scenario is the development of easy ways to get from program structure specification to the automatic or semi-automatic generation of diagnostic rules. Even more difficult and important is the twofold task of knowledge acquisition, finding articulate, self-analytical experts who know why they do things, and developing efficient techniques for extracting what they know and distilling it into rule bases. The essential prerequisite for building an expert system is to have an expert. The most powerful contribution of expert systems will surely be to put at the service of inexperienced programmer the experience and accumulated wisdom of the best programmers. This is no small contribution. The gap between the best software engineering practice and the average practice is very wide, perhaps wider than in any other engineering discipline. A tool that disseminates good practice would be important. Now we're talking. I think that using ChatGPT to help give you ideas on how to program something, rather than giving you the code itself, and asking it to like find errors for you, run test cases, see if your algorithms work the way you think they will, is the most efficient way to use an AI algorithm, right? And I think that especially for languages that you don't know very well, an AI like ChatGPT is going to be extremely helpful for you. Now, that's the end of the second recording. I will see you guys later. All right. Round 3, let's finish her off. Automatic programming. For almost 40 years, people have been anticipating and writing about automatic programming, the generation of a program for solving a problem from a statement of the problem specifications. Some people today write as if they expected this technology to provide the next breakthrough. Parnas implies that the term is used for glamour and not semantic content, asserting, in short, automatic programming has been a euphemism for programming with a higher level language than was presently available for the programmer. He argues in essence that in most cases it is the solution method, not the problem, whose specification has to be given. Exceptions can be found. The technique of building generators is very powerful, and it is routinely used to good advantage in programming or sorting. Some systems for integrating differential equations have also been permitted direct specification of the problem. The system assessed the parameters, chose from a library of methods of solution, and generated the programs. These applications have very favorable properties. The problems are readily characterized by relatively few parameters. There are many known methods of solving to provide a library of alternatives, and extensive analysis has led to explicit rules for selecting solution techniques given problem parameters. It is hard to see how such techniques generalize to the wider world of the ordinary software system, where cases with such neat properties are the exception. It is hard to even imagine how this breakthrough in generalization could conceivably occur. Interesting. Now, if we look at modern like LLMs that have like a portion of them like designed or oriented towards programming, say ChatGPT, Gemini, or like any of those ones, a lot of them do have the ability to generate a program simply by you telling them the problem, and like user stories and anything along those lines. But oftentimes it's not particularly good. Like, I wouldn't trust it. I do agree that like you basically have to tell it how to write the solution for you to want it, for it to come out the way you want it to. So yeah, that is an interesting problem, but I think it's one that may be resolved soon. So, but then again, we did just talk about how breakthroughs in software are slow. So anyway, graphical programming. A favorite subject for PhD dissertations in software engineering is graphical or visual programming, the application of computer graphics to software design. Sometimes the promise of such an approach is postulated from the analogy with VSLI chip design, where computer graphics plays so fruitful a role. Sometimes the approach is justified by considering flowcharts as the ideal program design medium and providing powerful facilities for constructing them. Nothing even convincing, much less exciting, has yet emerged from such efforts. I am persuaded that nothing will. In the first place, as I have argued elsewhere, the flowchart is a very poor abstraction of software structure. Indeed, it is best viewed as Burke's, von Neumann, and Goldstein's attempt to provide a desperately needed high-level control language for their proposed computer. In the pitiful multi-page connection box form to which the flowchart has today been elaborated, it has proved to be essentially useless as a design tool. Programmers draw flowcharts after, not before, writing programs they describe. Second, the screens of today are too small in pixels to show both the scope and resolution of any serious designed, detailed software diagram. The so-called desktop metaphor of today's workstation is instead an airplane seat metaphor. Anyone who has shuffled a lap full of papers while seated in a coach between two portly passengers will recognize the difference. Will not recognize the difference. One can see only a few things at once. The true desktop provides an overview of random access to a score of pages. Moreover, when fits of creativity run strong, more than one programmer or writer has been known to abandon the desktop for the more spacious floor. The hardware technology will have to advance quite substantially before the scope of our scopes is sufficient to the software design task. More fundamentally, as I have argued above, software is very difficult to visualize. Whether we diagram control flow, variable scope nesting, variable cross-references, data blow, hierarchical data structures, or whatever, we feel only one dimension of the intricately interlocked software elephant. If we superimpose all the diagrams generated by the many relevant views, it is difficult to extract any global overview. The VSLI analogy is fundamentally misleading. A chip design is layered two-dimensional object whose geometry reflects its essence. A software system is not. Now, as a computer engineer, I have worked with both System Verilog and more visual mediums of making PCBs and chips, right? And for that, wow. A graphical interface in that front makes it 10 times easier than using pure System Verilog. But for programming, I feel like graphical programming is a lot more feasible than he's making it out to be. Like, I think that like he focused too much onto the idea of something like a flowchart as a graphical programming, which is a way that we've used to express software, although I don't think it's efficient. But we have other methods, right? We like take a look at Scratch, right? Scratch is surprisingly powerful for what it is, right? Like people have made tons of things in Scratch, and if we would be able to make a more powerful version of Scratch that's basically a general compute, like a completely just like general programming language similar to Python, then I think we could have something on our hands. But as of now, I think he's right. In the future, I think he could be very wrong. Okay, program verification. Much of the effort in modern programming goes into testing and repair of bugs. Is there perhaps a silver bullet that can be found by eliminating the errors at the source in the system design phase? Can both productivity and product reliability be radically enhanced by following the profoundly different strategy of proving designs correct before the immense effort is poured into implementing and testing them? I do not believe we will find the magic here. Program verification is a very powerful concept and will be very important for such things as secure operating system kernels. The technology does not promise, however, to save labor. Verifications are so much work that only a few substantial programs have ever been verified. Program verification does not mean error-proof programs. There is no magic here either. Mathematical proofs also can be faulty. So whereas verification might reduce the program testing load, it cannot eliminate it. More seriously, even perfect program verification can only establish that a program meets its specification. The hardest part of the software task is arriving at a complete and consistent specification, and much of the essence of building a program is the fact that debugging of the specification. Interesting. I mean, this one is just like, it's hard to put it into words. It's true. Like, The easiest way to say this is that like it's yes, like this is just like a fundamental aspect of software engineering where it's just like you can't there's basically no way to figure out whether your program actually does what you think it does. Although some efforts have been tried, I know like basically like an idea of like general input has been like tried where you basically just put in like variables and just like figure out what the program does to them. But even then, that only works for like simpler programs, right? Like if you're displaying a bunch of images and like calculating a bunch of different values using like machine learning or something, it's not going to, that inherently is not going to work every single time, right? So let's move on to the next section. How much more gain can be environment and tools? How much more gain can be expected from the exploding researches into better programming environments? One's instinctive reaction is that the big payoff problems were the first attacked and have been solved. Hierarchical file systems, uniform file formats so as to have uniform program interfaces, and generalized tools. Language-specific smart editors are developments not yet widely used in practice, but the most that they promise is freedom from syntactic errors and simple semantic errors. Perhaps Perhaps the biggest gain yet to be realized in the programming environment is the use of integrated database systems to keep track of the myriads of details that must be recalled accurately by the individual programmer and kept current in a group of collaborators on a single system. Surely this work is worthwhile, and surely it will bear some fruit in productivity and reliability, but by its very nature, the return from now must be marginal. Jeez, I messed up that last part, but it's fine. Um, I mean, an environment can be a big part of efficiency. Sorry, not big, but like it can definitely be a part of your efficiency. Um, Personally, I prefer the JetBrains IDEs, but that's mostly because that they are quite feature packed. They are able to identify errors more readily, and that they have a good integration with the system. I know a lot of my friends use VS Code, and I kind of clown on them for using VS Code over JetBrains, but it is what it is. Workstations. What gains are to be expected for the software art from the certain and rapid increase in the power and memory capacity of the individual workstation? Well, how many MIPS can one use fruitfully? The composition and editing of programs and documents is fully supported by today's speeds. Compiling could stand a boost, but a factor of 10 in machine speed would surely leave the think time the dominant activity in a programmer's day. Indeed, it appears to be so now. More powerful workstations we surely welcome. Magical enhancements from them we cannot expect. I mean, yeah. Um, I know there has been talk about like ternary systems, where we have like instead of just zeros and ones, there's -1, 0, and 1, um, which could massively increase the efficiency of our current systems. But as of now, the likeliness that we adapt something like that and are able to, like, how do I put this? That we are able to transfer to that slowly while keeping both in line is unlikely. So it may be some time before we commit to a ternary system and figure out all the complexities of that. Promising attacks on the conceptual essence. Even though no technological breakthrough promises to give the soft note of magical results to which we are so familiar in the hardware era, there is both an abundance of good working going on. On now, and the promise of steady, if unspectacular progress. All the technical attacks on the accidents of the software process are fundamentally limited by the productivity equation. Time of task is equal to the summation of frequency times time. If as I have to believe, If, as I believe, the conceptual components of the task are now taking most of the time, then no amount of activity on the task components that are merely the expression of the concepts can give larger productivity gains. Hence, we must consider those attacks that address the essence of the software problem, the formulation of these complex conceptual structures. Fortunately, some of these are very promising. Buy versus build. The most radical possible solution for constructing software is not to construct it at all. Every day, this becomes easier as more and more vendors offer more and better software products for a dizzying variety of applications. While we software engineers have labored on production methodology, the personal computer revolution has created not one, but many mass markets for software. Every newsstand carried monthly magazines which, sorted by machine type, advertise and review dozens of products at every price from a few dollars to a few $100s. More specialized sources offer very powerful products for the workstation and other Unix markets. Even software tools and environments can be bought off the shelf. I have elsewhere proposed a marketplace for individual modules. As such, a product is cheaper to buy than to build afresh. Even at a cost of $100,000, a purchased piece of software is costing only about as much as one programmer a year, and delivery is immediate. Immediate, at least for products that really exist, products whose developer can refer to the prospect to a happy user. Moreover, such products tend to be better documented and somewhat better maintained than homegrown software. The development of the mass market is, I believe, the most profound long-run trend in software engineering. The cost of software has always been a development cost, not a replication cost. Sharing that cost among even a few users radically cuts the per user cost. Another way of looking at it is that the use of n copies of a software system effectively multiplies the productivity of its developers by n. That is an enhancement of the productivity of the discipline of the nation. The key issue of course applicability. Can I use an available off-the-shelf package to do my task? A surprising thing has happened here. During the 50s and 60s, study after study showed that users would not use off-the-shelf packages for payroll, inventory control, accounts receivable, etc. The requirements were too specialized, the case-to-case variation too high. During the 1980s, we find such packages in high demand and widespread use. What has changed? Not really the packages. They may be somewhat more generalized and somewhat more customizable than formerly, but not much. Not really the applications either. If anything, the business and scientific methods of today are more diverse, more complicated than those of 20 years ago. The big change has been in the hardware-software cost ratio. The buyer of a 2 million machine in 1960 felt that he could afford $250,000 more for a customized payroll program, one that slipped easily and non-disruptively into the computer-hostile social environment. Buyers of $50,000 office machines today can't conceivably afford customized payroll programs, so they adapt their payroll procedures to the packages available. Computers are now so commonplace, if not yet so beloved, that the adaptations are accepted as a matter of course. There are dramatic exceptions to my argument that the generalization of software packages has changed a little over the years. Electronic spreadsheets and simple database systems, these powerful tools, so obvious in retrospect and yet so late appearing, lend themselves to myriad uses, some quite unorthodox. Articles and even books now abound on how to tackle unexpected tasks with a spreadsheet. Large numbers of applications that would formerly have been written as custom programs in COBOL or a program generator are now routinely done with these tools. Many users now operate their own computers day in, day out on varied applications without ever writing a program. Indeed, many of these users cannot write new programs for their machine, but they are nevertheless adept at solving new problems with them. I believe that the single most powerful software productivity strategy for man organization today is to equip the computer-naive intellectual workers on the firing line with personal computers and a good generalized writing, drawing, file, and spreadsheet system to turn them loose. The same strategy with simple programming capabilities will also work for hundreds of laboratory scientists. Now we're getting into what has made computers really ubiquitous over the past few years, right? Now, buying packages such as like Microsoft 365 or like Google Drive, which like comes with like sheets, docs, slides, that's so on, right? Those are the packages that many of us use on an extremely daily basis, right? Like I don't think I can even count the number of times I've had to make a presentation for class and use either slides or PowerPoint, right? And I'm sure a lot of office workers, scientists, everything along those lines use Excel a lot. Um, I do find it interesting that he emphasized the idea of the spreadsheet so much. I mean, it definitely is a really big innovation and definitely helps a lot of people figure out like certain aspects, make large calculations easier. But even then, I feel like there is definitely some other big ones that he could have focused on that is less mundane than a simple spreadsheet, right? But that's just my opinion. I do also find it interesting that people started buying packages for their computers because their computers got cheap. Um, but yeah, I think that today, like a lot of us, I mean, especially people who don't use programming very much, um, their taskbar won't look like mine, right? Like you won't see like Unity, a bunch of IDEs on it, right? Like GitHub, that sort of thing. Um, you'll see like Chrome, Spotify, like a lot of these like just like stuff that's just like pure applications, right? They're intended to help the user do what they want to do with their computer, right? Instead of just programming the computer to do what they want to do. All right, moving on. Requirements, refinement, and rapid prototyping. The hardest single part of building a software system is deciding precisely what to build. No other part of the conceptual work is too difficult as establishing the detailed technical requirements, including all the interfaces to people, to machines, and to other software systems. No other part of the work so cripples the resulting system if done wrong. No other part is more difficult. Go rectify it. Okay, I'm assuming that means to rectify later. Therefore, the most important function that software builders do for their clients is the iterative extraction and refinement of the product requirements. For the truth is, the clients don't know what they want. They usually do not know what questions must be answered, and they almost never have thought of the problem in detail that must be specified. Even the simple answer, make the new software system look like our old manual information processing system, is in fact too simple. Clients never want exactly that. Complex software systems are moreover things that act, that move, that work. The dynamics of that action are hard to imagine, so in planning any software activity, it is necessary to allow for an extensive iteration between the client and the designer as part of the system definition. I would go a step further and assert that it is really impossible for clients, even those working with software engineers, to specify completely, precisely, and correctly the exact requirements of a modern software project before having built and tried some versions of the product they are specifying. Therefore, one of the most promising of the current technological efforts, and one which attacks the essence, not the accidents, of the software program, is the development of approaches and tools for rapid prototyping of systems as part of the iterative specification of requirements. A prototype software system is one that simulates the important interfaces and performs the main functions of the intended system while not being necessarily bound by the same hardware speed, size, or cost constraints. Prototypes typically perform the mainline tasks of the application, but they make no attempt to handle the exceptions, respond correctly to invalid inputs, abort cleanly, etc. The purpose of the prototype is to make real the conceptual structure specified so the client can test it for consistency and usability. Much of present-day software acquisition procedures rests upon the assumption that one can specify a satisfactory system in advance, get bids for its construction, have it built, and install it. I think this assumption is fundamentally wrong and that many software acquisition problems spring from that fallacy. Hence, they cannot be fixed without fundamental revision, one that provides for iterative development and specification of prototypes and products. No, I think this is one that like we're readily addressing in 2340, right? With the idea of making prototypes, specifically with like the idea of agile and like keeping the customer in the loop in terms of your programming. I think this one is like basically like embodying that idea of agile, right? So it's definitely something that we're using right now, right? It's definitely something that's making software engineering and communication between um, programmer and buyer more efficient. Whoops. Excuse me. Incremental development, grow, not build software. Incremental development, grow, not build software. I still remember the jolt I felt in 1958 when I first heard a friend talk about building a program as opposed to writing one. In a flash, it would be broadened by my whole view of the software process. The metaphor shift was powerful and accurate. Today, we understand how, like other building processes, the construction of software is, and we freely use other elements of the metaphor, such as specifications, assembly of components, and scaffolding. The building metaphor has outlived its usefulness. It is time to change again. If, as I believe, the conceptual structures we construct today are too complicated to be accurately specified in advance and too complex to be built faultlessly, then we must take a radically different approach. Let us turn to nature and study complexity in living things instead of the dead works of man. Here we find construct whose complexities thrill us with awe. The brain alone is intricate beyond mapping, powerful beyond imitation, rich in diversity, self-protecting, and self-renewing. The secret is it is grown, not built. So it must be with our software systems. Some years ago, Harlan Mills proposed that any software system should be grown by incremental development. That is, the software system should be first made to run even though it does nothing useful except call the proper set of dummy subprograms. Then bit by bit it is fleshed out with the subprograms in turn being developed into actions or calls to empty stubs in the level below. I've seen the most dramatic results since I began urging this technique on the project builders in my software engineering laboratory class. Nothing in the past decade has radically changed my own practice or its effectiveness. The approach necessitates top-down design, for it is a top-down growing of the software. It allows easy backtracking. It lends itself to early prototypes. Each added function and new provision for complex data or circumstances grown organically out of what is already there. The morale effects are startling. Enthusiasm jumps when there is a running system, even a simple one. Efforts redouble when the first picture from a new graphics software system appears on the screen, even if it is only a rectangle. One, uh, one always has, at every stage in the process, a working system. I find that teams can grow much more complex entities in 4 months that they can build. The same benefits can be realized on a large products as on my small ones. Interesting. Um, I agree with like the aspect of that f- that feeling of finishing a certain aspect of your program, even if it's like an extremely small one, right? Like when I was programming my first VR video game, just getting the program to recognize like where my hands were, right? Because we were building a controllerless input system, right? So getting the headset to see where my hands were and porting that into VR so I could just like look in the headset and see where my hands were was was beyond satisfying, right? That was like that was like one of the top moments of that project, I'd say. But I agree. Incremental development is important, right? We can't build an entire program in one night. Although I've definitely done that with a few homework assignments. But honestly, like I feel like that this feels obvious today, and that's a good thing, right? Because we want stuff like this to be widely used, right? To be just how we address things nowadays. So, yeah. let's move on. Great designers. The general question of how to improve the software art centers is always on people. We can get good designs by following good practices instead of poor ones. Good design practices can be taught. Programmers are among the most intelligent part of the population, so they can learn good practice. Thus, a major thrust in the United States is to promulgate good modern practice. New curricula, new literature, new organizations such as the Software Engineering Institute have all come into being in order to raise the level of our practice from poor to good. This is entirely proper. Nevertheless, I do not believe we can make the next step upward in the same way. Whereas the difference between poor conceptual designs and good ones may lie in the soundness of the design method, the difference between good designs and great ones surely does not. Great designs come from great designers. Software construction is a creative process. Sound methodology can empower and liberate the creative mind. It cannot inflame or inspire the drudge. The differences are not minor. It is rather like Salieri and Mozart. Study after study shows that the very best designers produce structures that are faster, smaller, simpler, cleaner, and produced with less effort. The differences between the great and the average approach an order of magnitude. Sure. A little retrospection shows that although many fine, useful software systems have been designed by committees and built by multi-part projects, those software systems that have excited passionate fans are those that the products of one or a few designing minds, great designers. Consider Unix, APL, Pascal, Modula, the Smalltalk interface, even Fortran, and contrast with COBOL, PLI, Algo, MVS 370, and MS-DOS. Hence, although I strongly support the technology transfer and curriculum development efforts now underway, I think that the most important single effort we can mount is to develop ways to grow great designers. No software organization can ignore this challenge. Good managers, scarce though they are no scarier than good designers, or no scarcer than good designers. Great designers and great managers are both very rare. Most organizations spend considerable effort in finding and cultivating the management prospects. I know none that spends equal effort in finding and developing the great designers upon whom the technical excellence of the products will ultimately depend. The first proposal is that each software organization must determine and proclaim that the great designers are as important to its success as great managers are, and that they can be expected to be similarly nurtured and rewarded. Not only salary, but the prerequisites of recognition, office size, furnishings, personal technical equipment, travel funds, staff support must be fully equivalent. How to go great designers? Space does not permit a lengthy discussion, but some steps are obvious. Systematically identify top designers as early as possible. The best are often not the most experienced. Assign a career mentor to be responsible for the development of the prospect and keep a careful career file. Devise and maintain a career development plan for each prospect, including carefully selected apprenticeships with top designers, episodes of advanced formal education, and short courses, all interspersed with solo design and technical leadership assignments. Provide opportunities for growing designers to interact with and stimulate each other. I think he's basically just like circling back to the fact that the best way to design a program is to do it through a person, right? He talked about AI, right? He talked about all of these different practices and systems that we attempted to make programming easier, right? But at the end of the day, the best way to make a good program is just to be a good programmer, right? And I think that comes down to I think that one idea that I do disagree with here, though, is the idea that some of these people are inherently talented, right? I don't think anyone is really inherently talented at making software, right? It's not something that like you basically are like in 7th grade, and you just like magically boot up a computer and are able to design a program that is able to do things that nobody has ever seen before, right? Um, but there definitely is an aspect of talent to it, right? The idea, the ability to be able to think in that abstract aspect of like class structures and everything along those lines, right? And be able to basically come up with a solution like that, right? But still, I think that we should make it our effort to develop a way to create great designers instead of just being able to identify them, right? And if we're able to create great designers, right, then it nulls the need for program generation by either inexperienced hands or AI or something along these lines, right? But at the end of the day, we're studying computer science for a reason, right? We want to become these great designers that this paper mentions. So I think that learning the practices of software engineering like we are in 2340 is important, and that it needs to be something that's more emphasized in a lot of computer science education programs. So, yeah. But that is the end of the paper. So that is it. Thank you guys for watching. I hope you enjoyed my reading and reflection on this paper. Um, this video is probably going to be like 80 minutes long. So, yeah, right. Thank you.